In this video, we will learn about the cement, its type, what are the types of cement we use based on its composition, Portland cement, the widely used cement in the world, the types of cement based on their usage and chemical composition, either it's ordinary Portland cement, either it's rapid hardening cement, low heat cement, sulfate resistant cement. We'll discuss all these in detail. Um, After that, we will discuss the manufacturing of Portland cement, what manufacturing process involved in the manufacturing of Portland cement, its raw material composition, its crushing and grinding of primary raw materials, methods involved in grinding and crushing of these materials. Then the cement processes, the burning process involved, the burning temperatures, burning regimes, burning shape, type of the burning kiln, and then the grinding of the clinker, and lastly the storage, packing and dispatch, and the manufacturing scheme of cement. Lastly, we will discuss the chemistry, the chemical composition of the cement, and its few of the properties, physical chemical properties of the cement uh, that totally depends upon it, that defines the quality of a cement and type of a cement, what cement we have to adopt, we have to use for the specific applications. For example, you are using um, you require to have a concrete with a strength around 800 pi 8000 psi, very high strength concrete you need. Then what type of a cement and what ingredients that you have um, to formulate your cement. So this is a brief introduction of today's lecture that we are going to cover. Cement. Cement is basically the mixture of calcareous and argillaceous rocks. Calcareous are calcium rich, which are basically limestone is rich in calcium, which can be found in the Earth's crust and throughout any geology. Either if you are in Asia, if you are in America, if you are in Australia, you will have a geology. You have a calcium rich rocks. Either these are the limestone, either these calcareous origin can be taken from the some um, sea origin, like you can use the shells. Uh, then you have a argillaceous rocks. Argillaceous rocks are basically the combination of a uh, siliceous and aluminous material. So argillaceous might be of any clays. There are the vast majority of clays in that you can use in cement. Clays have a lot of silica content and alumina content and some alkali earth materials in it. So you first refine that clays based on your requirement, how much of the constituent do you need for cement production. Then you combine these calcareous and argillaceous materials itself and grind it, um, and then you fuse that material by at a higher temperature at about 1450 degrees Celsius, so that these materials can gain the sintering. Um, After the grinding process, the cement is converted into some um, small ball-like shapes known as clinkers. And after the clinker production, you allow the clinker to cool down, sufficiently cool down, and then grinding of the clinker takes place with some addition of a gypsum to be added depending upon the requirement. How much do you want to give the open time to the cement? So basically, these are the constituents: calcareous and argillaceous materials or rocks can be used in as a prime source of raw materials. Secondly, cement is hydraulic binder basically. Hydraulic binder is a type of a binder which can gain gain strength in the presence of water. Without water, it retards its strength. It depletes its water within the mix. It is compulsory to have a water for its hydration reaction. So it is a hydraulic binder, cement. Cement and lime, both cement and lime are hydraulic binder. We will discuss later about the lime. Um, so cement is defined as a finely ground inorganic material which, uh, when mixed with the water, that forms a paste and sets and harden by means of hydration reaction and processes. After hardening, retains its strength and stability under water. So hydraulic binder means it have to have uh, it would gain strength in the presence of water. So cement is a very popular building material in the in conventional concrete technology and in modern concrete industry by the so cement is using in any shape. It's either in OPC and or any other types that we will discussing in later on in this video. The cement bind basically the aggregate phases itself and with among the aggregate particles. It also fills the spaces between the fine aggregate and the coarse aggregate. Um, you have in your concrete mix, you can imagine that you have a 50 to 60% of your coarse aggregate and 20 to 30% of a fine aggregate and 10 to 15 to 20% of your binder, and that is conventional concrete cement. So the spaces between the coarse aggregate are filled by fine aggregate particles or some type of fillers. Um, the spaces are and there are quite wider spaces in among the aggregate particles. For example, the maximum size of aggregate that you use is around 19 millimeters, let's say, maximum nominal maximum size. Um, First, you must have an idea about the nominal maximum size. Nominal maximum size is basically the maximum size of aggregate, the maximum size of a sieve opening by which the all aggregate passes. So it's a nominal maximum size. You should have a basic idea of different definition that I will be giving you while delivering this lecture. In case of any questions, you might or you can ask your questions and any queries in the comment section so that you can have a clear idea about this lecture. So I was talking about the gradation and the pores between the coarse and fine aggregates. So 60 to 70% the aggregate are in adequate amount in abundance. Aggregates present in concrete are in abundance. So the aggregate size is quite larger than the all other constituents, like you have a cement, sand, or any other filler. The average aggregate size of a cement is around 30 microns, which is quite low. While you see the average particle size of sand, it would be around it might be around zero point 0.6 or zero point 0.7 millimeters. If you talk about the average particle size of a coarse aggregate, it would be exponentially higher than these fillers and binders. So coarse aggregate have a larger size, and the space among the coarse aggregate particles is also too higher. So we use some inert fine aggregates or some fillers to fill that macro pores among the coarse aggregate particles, so that we can have a pretty good cement paste matrix. So by using a sand or any other type of filler, you have occupied your coarse or micro-sized voids. What about the micro-sized voids that are being created um, among the fine aggregate particles? So these voids can be filled by some binders that you are using. In this case, cement particle whose average particle size is around 30 microns would occupy the spaces between the fine aggregate and the matrix, so that you can have a adequate density of a cement to be called as a concrete. So this was a brief introduction about the cement and concrete. Um, I will create the correlation between the different properties of a cement, but that are correlating with with that of concrete. So the type of a cement that you use is hydraulic cement. There is also a non-hydraulic cement, which do not depend upon the water or water cement ratio, incorporated water cement ratio, or actual water cement ratio for the strength and strength gain. These cements may be like gypsum plaster or some um, plaster of Paris type cements that do not require any water for its hydration. So the hydraulic cements, the normal conventional cement I am talking about, the hydraulic cements require the water for the hydration. The chemical reaction involved in the hydration reaction basically requires the water for its completion or a strength gain. Basically, I will talk about different hydration products that are resulting as a result of hydration products in later slides. But in this, I will cover the general concepts about hydraulic cement. Hydraulic cement may be Portland cement, natural cements, expensive cements, and high alumina cements. Portland cement contains, if we talk about the chemical composition of a Portland cement, it's a normal cement which contains the calcareous rocks. I mean the calcium carbonate, which can be obtained from a limestone or from any other source, like you are using a seashells, or and for the argillaceous materials, you can use the silica, alumina-rich iron minerals. You can use clay, shale, and such other rocks which contains a high constituents of higher composition, higher amount of silica and alumina in it. So the calcareous and argillaceous rocks, when mixed and heated, it became the clinker. The clinker then formed is basically in the formation of clinker. It involves a lot amount of energy to be required. It takes around 1450 degrees Celsius to form the clinker. So in cement production, there is a lot of fossil fuel consumption and a lot of energy required for the production of a cement that involves an enormous amount of carbon footprints and cause of global warming. So in the cement production, conventional cement production is a threat to the sustainability, and it causes the global warming. So scientists are trying their best to invent or to partially replace the modern cement with some innovative and sustainable cements, so that they can have a lower impact of carbon emissions on their um, economy on and environment can be protected. So it's a composition. This slide shows the composition of cement. It contains quicklime, calcium oxide of very high proportion 60 to 65% of the calcium can be utilized based on your chemical composition. The silica is a second most abundant compound present in the cement. Thirdly, the aluminum oxide, 4 to 8%. The use of aluminum oxide is recommended. And then the iron oxide, 2 to 4% of iron oxide, and magnesium oxide, and gypsum. So, the significance of using these minerals are basically related to the different phenomena occurred in hydration reaction that we will be discussing in this lecture. Uh, these basically are the chemical compositions. Uh, these are the added added oxide composition in your cement. Uh, so the uh, so the products mentioned over here are the compounds which are formed as a result of a clinker manufacturing and grinding. So I will discuss it in manufacturing of a cement, but over here I want to show the significance and importance of each constituent over here. You have mainly you have a four main constituent in ordinary Portland cement or any type of a cement you have. Firstly, the tricalcium silicate. Secondly, the dicalcium silicate. Thirdly, the tetracalcium aluminoferrate. Fourthly and lastly, the tricalcium aluminate. These constituents are very important in hydration reaction and in different phenomena involved in hydration reaction. Um, for example, the tricalcium silicate uh, take parts in early hardening of cement. Tricalcium silicate (C3S) is used basically the early hardening of cement. Secondly, the dicalcium silicate contributes toward the hydration reaction at later ages like above 50 days or more than when you have a concrete at more than 28 days, then the strength gain in that concrete would be due to this component, that is dicalcium silicate. Thirdly, it has a tetracalcium aluminoferrate, and fourthly, the tricalcium aluminate. These phases are used for these phases take part in setting of cement. These both products. In early strength gear setting or a setting of a cement, the tricalcium aluminate takes part. Basically, there is a difference between the setting and hardening of cement. In hardening of cement, cement gain its strength and cement gain its ability to take loads. While on the other hand, setting is basically the loss of flow is setting. Chemically, if we talk about chemical in chemical language, what is the setting and what is the hardening? I want to I want to show you these some images. These are scanning electron images of the hardened concrete. These are the some images of hardened concrete. You can see a lot of hydration products as a result of a hydration reaction. Basically, it contains the different products that you can identify based on their shapes. Um, Other than shapes, these also can be identified based on their chemical composition while taking these SEM images. Chemical composition in SEM images can be determined by the EDX analysis, which is energy dispersive X-ray spectrometry. Basically, in SEM analysis, you have a non-photographic based SEM analysis. You don't have a camera image, a camera lens, so that you can take this SEM images. You just utilize the high energy electron beams to be bombarded on your specimen. so that it can have an morphology of the specimen by imaging without camera-based imaging. So after bombarding high electron beams on the specimen, the electron beams passes through the specimen and received at the receiver of the in the electron microscope. The image would be formed, and this image will show this morphology based on their electron beams, information gained by the electron beam. So over here we have some needle-like shapes, needle-like microstructure, and some gel-like microstructure can be seen in this micrograph over here. Um, the gel-like microstructure shows the CSH calcium silicate hydrate, which contribute toward the strength gain of a concrete. While you can see the needle-like structure over here, the needle-like structure shows the basically is the attringite formation. Calcium silicate hydrate is a component formed which contribute towards the strength gain of a concrete. On the other hand, the attringite needles it imparts the setting of concrete. As you can see that the needle-like structure will retard the flow of concrete, and it hindered the flowability of a concrete by the formation of needle-like structure. On the other hand, the flaky or hexagonal structure, basically calcium hydroxide is the hexagonal structure in the microstructure. You can see over here the hexagonal, some flaky type structure. It might be a calcium hydroxide, but it is confirmed that in this region you have a calcium hydroxide. Basically, the calcium hydroxide has a perfectly hexagonal structure. Um, these do not contribute toward the strength of a concrete. Basically, it's a byproduct that is formed in the hydration reaction. So this byproduct is vulnerable to the leaching. In case of a CSH and a tringite, these are the very stable products. These products cannot leach or mix with the water being intruded into the concrete. While on the other hand, the calcium hydroxide have an ability to dissolve in the water in case of intrudement of water into the concrete microstructure, so that with the passage of a time your concrete would be a little porous, and it would be um, susceptible to freezing and thawing, and you know degradation with time and environment. So in this same image, you can see the hydration products very easily. And I was talking about last two hydration products, which are tricalcium aluminate and tetracalcium aluminum ferrite. So tricalcium aluminate imparts the early setting of a cement. On the other hand, tetracalcium aluminum ferrite imparts the final set of a cement. By the hydration of a tricalcium aluminate, you will get the attringite needles, these attringite needles. On the other hand, by the hydration of a tricalcium silicate, you will get the CSH gel-like microstructure, and formation of a calcium hydroxide. These are the products of the hydration reaction. On the other hand, the hydration of the dicalcium silicate would involve at later ages. The microstructure formed by the dicalcium silicate would be similar to that of the former one, but it would at later ages. Uh, Moreover, it is hard to identify the hydration products of both calcium silicates. On the other hand, the hydration products of these can be easily distinguished based on their morphology and shape. So the Portland cement is obviously I have talked a lot about the hydraulic cement. So it gains strength by the by the precipitation of calcium silicate hydrates in cement paste matrix, so that um, the water resistance product is formed. So the calcium silicate hydrate also contribute um, toward the toward reducing the permeability of a concrete by calcium silicate hydrate production. So in this second micrograph, I want to show the how much cement can be hydrated. According to the literature, cement only hydrate around 20%, depending upon its particle size. If you grind if you grind cement uh, in a very minute particle size, lesser than let's say 10 micron, it would have a higher rate of hydration, because the more the surface area you have, more would be the reaction, more would be the vulnerability to get the reacted. So the cement particles only hydrate up to 20%. You can see in the same micrograph over here that cement grain is still intact, and 20% of the its upper 20% of its upper region is being hydrated into some sort of a gel and crystals. So these formation of a gel and crystal will contribute toward the strength gain. So uh, these are the microstructure studies of the cement. Here you have an equation that limestone-rich, calcium-rich rocks with alumina-rich rocks upon heating would create the clinker, and it exits the large amount of carbon dioxide into the atmosphere and other harmful gases. This is very interesting slide. I basically love it. In this slide, you can see the Roman concrete, and Roman monumental structures like Pantheon Dome. It is basically unreinforced dome. It do not contain any of the steel. You can also see that section of this dome. The Roman technology, or Roman engineers or architects. Engineers were so intelligent that at that time they know about the how the stress were transmitting through this dome or through arch action. They just conceptualize the things, and they use a very lightweight materials to build this dome. Probably in this dome they have used volcanic ash, volcanic tuffs as a fine and coarse aggregate respectively, and they used volcanic ash as a um, binder, and they have an aggregate of volcanic tuffs. They are very lightweight aggregates. They can they have a very lower dead load as compared to normal concrete. So the basic concept involved in the formation of a Pantheon dome was to minimize the dead load, so that you don't have to fight against the loads which are caused due to gravity. So by reducing the self weight, they were able to build such a monumental Pantheon dome, which still exists. Um, in second image, you see that I can see the lightweightness of this binding material by their texture. So the evidence of a Roman lightweight concrete can be seen in this image. It's a Roman concrete. It contains a very lightweight coarse aggregates, as well as a five fillers. They use volcanic ash and some pozzolanic material. They use a lime and volcanic ash as a binders, so that they can achieve the very lightweightness of that concrete. So these are the Roman concrete structures which are which I have described. Um, in Portland cement, uh, I have the I have explained the composition of a Portland cement. Uh, well, if you define the different types of cement, these cement are based on their applications. They are based on their they are based on their admixtures. Sorry, additives. Um, let's say we have a ordinary Portland cement. These are known as this is known as the type 1 cement. According to ASTM classification, type 1 cement have a strength gain at the 28 days strength. We will call it design strength. Uh, there is a ordinary Portland cement. Secondly, you have a moderate sulfate resistant cement. It would resist in sulfate resistance. Um, it has a tricalcium aluminate phase less than 7%. Basically, the tricalcium aluminate caused the delayed Achinchite formation by the action of external intrusion of some sulfate salts. When you have a sulfate solutions, when you have a structure built within the seabed, or you can say that it is interacted with the soil, which have a permeable soil, so that the sulfates can intrude into the concrete. So in moderate sulfate resistance cement, you limitize the concentration of a tricalcium aluminate. Tricalcium aluminate, if you have a unreacted tricalcium aluminate in the concrete mix, it would react with the external intruding sulfate salts that will cause the delayed Achinchite formation when concrete is hardened. So in the hardened state, the delayed Achinchite formation, basically Achinchite is expensive, very expensive product. So no, expensive mean expands. But by the formation of a tricalcium aluminates, the concrete volume expands internally. So when the concrete is hardened, the the formation of a delayed Achinchite formation occurred, then it might create a lot of cracks into the cement paste matrix and almost destroy the concrete. So in regions where you have a lot of chance of a sulfate attack, then you restrict the amount of a tricalcium aluminate. So in type 2 cement, it's a moderate sulfate resistant cement. In type 3 cement, you are you are basically increasing the concentration of a tricalcium silicate. I have mentioned earlier that the tricalcium silicate contribute toward the early strength gain of concrete. So if you increase this constituent, then the concrete would have a higher strength, a higher earlier strength. So it's rapid hardening cement. It's not a rapid setting cement. Hardening and setting, since the hardening and setting are the different phenomena involved in in hydration reaction. So fourthly, it's a low heat Portland cement. It has a very low amount of heat, hydration heat evolved as a result of hydration. In fact, it has a very slow early strength gain. Uh, it has used in the wide applications, like if you are concreting in a very harsh, a very um, um, high temperature environments, then you will use a low heat cement. If you use the normal OPC cement in a very high ambient temperature environment, it would crack, it would shrink, it would not satisfy the all the requirement of the concrete. Like it may be cracked, it may have it may have generated a lot of hydration energy, hydration heat of hydration, that it may have a very high shrinkage cracks on the surface. So is the durability, very less durability. So lastly, we have a high sulfate resistance Portland cement. So it's a cement to be used in the regions where have a very high probability of a sulfate attack. So you will use sulfate resistance. It would have a tricalcium aluminate content less than 3% or less than 3.5%, so that the unreacted tricalcium aluminate would be limitized in cement paste matrix. So along these five types, these are the conventional types normally used in everywhere. Alongside these types, there are other types of a cement, that is Portland blast furnace cement, pozzolanic cement, air entrant cement, and white Portland cement, colored Portland cement. So you have all these types basically when these are required. Let's say you have a very durable type of a cement that you want, very durable type of a concrete in your construction that would have a higher durability. Normally we talk about the strength of a concrete. Uh, I agree that the if you have a high strength, it would have have higher durability associated with it, but the durability is not as simple as the strength. You cannot always predict the strength with the durability. If you durability is associated with the the resistance being offered by a concrete toward the external agents. The external agents might be some type of acid rains, some type of sulfate salts, some type of other salts like saline salts, sodium hydroxide, calcium hydroxide, and these are or a penetration of some chemicals. I mean the attringite, which is formed as a result of a higher expansion, which causes the cracks. The cracks induces a durability problem. So you have a concrete with the age of a concrete, the life of concrete reduces due to the durability aspects. Then it's a chemical composition based, the type of a cement based on their chemical composition that I have explained. So if you're using the type 1 cement, it's a general purpose cement. It has a fairly high amount of a tricalcium silicate. It would achieve the strength within the 28 days. On the other hand, if you have a moderate sulfate resistant cement, it would have a tricalcium aluminate content lesser than 8%, uh, so that the surplus tricalcium aluminate would not be there in the cement matrix to induce delayed attringite formation or some other durability problems. Thirdly, you have a high strength cement which have a high amount of a tricalcium silicate, which increases the early strength gain. Uh, Fourthly, you have a low heat cement that are used with considerably lower tricalcium silicate content. So, lastly, you have a high resistance cement, high sulfate resistance cement uh, to be to be used um, in marine environment and or environment which is fairly exposed to sulfate attack. So the application of these cement involves Lloyd cement. These are used in mass concrete structures. Mass concrete structures are those structures which have a dimension, either of the dimension more than 1 meter. So type 3 cement, rapid hardening cement. Low-heat cement can also be used in some um, temperature, very high temperature. If you have a very high temperature, ambient temperature on which the concrete is being casted, then you should have to use low-heat cement or some alternative of ordinary Portland cement. Some um, if you are concreting in very cold region, um, you can use high early strength or rapid hardening cement, so that uh, cement would gain the strength earlier, because the hydration reaction is totally dependent upon the ambient temperature. If you have a temperature around 35 to 40 degrees Celsius, it would be a very uh, this temperature is basically an very conducive temperature to initiate the rate of hydration. So if you exceed the temperature, if you increase the ambient temperature, it would accelerate your hydration reaction. But at the time reaches, there is a limit at 60 degrees Celsius. You would have a hydration reaction totally retarded. So you have to give a ambient temperature to the concrete so that it can have a reaction with the desired rate. If it would be a quite slower, it would not get the adequate strength, or it would cause some durability issues. If uh, the rate of a reaction is so fast, it would evolve an enormous amount of hydration energy, and it cracks the concrete microstructure. So in this chart, you can see the chemical composition of these five cements. In general purpose cement, you have these constituents in these percentages: a log. Um, in a second type of a cement, moderate sulfate resistant cement, you have a decreased amount of tricalcium aluminate because of the probability of a delayed adenine formation as a result of a sulfate intrusion. Thirdly, you have a early strength cement. You have a higher concentration of tricalcium silicate, and you can gain the early hardening, early strength by grinding this material, tricalcium silicate, so that it can um, have higher hydration of a cement particles that I have talked earlier about, that cement only hydrates up to 20%. If you decrease the particle size, it would have a higher strength. At the fourth number, you have a low heat cement. The amount of tricalcium silicate which contribute towards initial strength gain is quite lower. On the other hand, the dicalcium silicate, the concentration is quite higher. That's why it is low heat cement. It evolves low heat as a result of hydration reaction. Lastly, you have a sulfate resistance. High sulfate resistance cement has a tricalcium aluminate content less than 4%. This is basically a colorimetric curve uh, used to gauge the heat of hydration of a cement. Um, the moment this water is added into the cement paste, um, the hydrolysis occurs. The curve in the stage one shows the hydrolysis of a cement. Hydration, water is added into the cement paste. So the heat is basically evolved as a result of hydrolysis. In the second stage, you can see it's a dormant period, or you can say induction time. Dormant period is that period in which the cement paste sets or start to sets. Between the dormant period, you can see that it shows the initial and the final set of a cement. In stage 3 and 4, the strength gain and the final setting of the cement occurs. So you can see that the tricalcium silicate hydration occurs at the top of this curve, and tricalcium aluminate over here at the final set of a cement. At the later stage, stage, the hydration occurs at the later ages. Like you have a 28 age compressive strength of a concrete at a more than a 25 at higher ages, it would contribute toward the stage 5. So rapid hardening cement contains the very higher surface area and a very minute particle size as compared to the OPC. It could have tricalcium silicate, a higher concentration of a tricalcium silicate that I have explained earlier. Um, this cement can be used if you are using your formwork. When you want to remove your formwork in very earlier, then you can use a rapid hardening cement. Or when you're using cold weather concreting, then you can also use this type of a cement. This type of cement would in cold weather concreting, it would resist the frost action, or you can say freezing thawing cycles of the concrete, because it would gain the earlier strength, so that water could not be penetrated into the cement mix, and due to the due to the early hydration, it would gain the desired strength and durability, so that it could not be damaged by the frost action. So ultra high strength cement, it has a very higher surface area. Normally you have a surface area of around 2200 centimeter square per gram in case of a OPC. In this case you have a 7000 to 9000 centimeter square per gram of a surface area in early high strength cement type. So this is a huge comparison. This is a huge exponential increase of a surface area that would contribute towards the strength gain. So it would contribute toward ultra high strength of a concrete. So you can play around the different chemistry and the particle size of a constituent if you require the ultra high strength cement, or extra rapid hardening cement, or early setting cement. You would have a understanding about the chemistry and the physical properties of um, cement, so that you can alter these chemical composition and particle size, so that it can have a desired properties um, for desired application. So in extra rapid hardening cement you can use some type of accelerator. In rapid hardening cement, you can use some type of accelerator. Calcium chloride is some old version accelerator that nowadays cannot be used in reinforced concrete because of a chloride content. Basically, chloride induce the corrosion. Basically, chloride is a corrosion inhibitor in concrete. It induces the corrosion on the steel bars in the reinforced concrete, thus reducing the design age of the structure. So, calcium chloride cannot be used in reinforced concrete. Nowadays, there are several. Nowadays, after invention of admixtures, so plasticizers, there are various type of admixtures that you use in the concrete in modern concrete industry. So, calcium chloride is basically obsoleted. Rapid extra hardening cement type used in, let's say, where you have a very less amount of open time. Basically, open time is a time that you require to make your uh, make your structure serviceable. Let's say I have an airport to be maintained, so that it can uh, it can serve after the maintenance. Right, I have a open time of 3 hours. It means that I have to have my all the procedures of concreting, finishing, hardening, everything completed within first 3 hours. So it is very difficult to cater all the other consequence of extra rapid hardening Portland cement, because when you increase the rapid hardening, it induces several other problems, like it would cause shrinkages, different shrinkages. It would reduce the cracks. It may be cracked due to thermal stresses, or heat of hydration evolution. So it is very difficult to have a extra rapid hardening cement to be utilized in your structures. It takes a lot of expertise and experience to use this type of cement in um, in different structures.